Hello, everyone, and welcome back to Creation Myths. Today, I am going to show you a debate that I had with professional young Earth creationist Dr. Jerry Bergman on the Standing for Truth channel on January 18th, 2025. Yes, I went on SFT for this debate. I was actually invited to participate in this debate, and the fact of the matter is, most young Earth creationists aren't going to leave creationist spaces to talk to people. So if I want to talk to them, I have to go where they are. So that's what I did. We had this debate. The topic was common descent versus common design. And I'm going to play it for you here in its entirety. I think it went really well. I tried something a little bit different with my opening, the way I structured my argument from what you normally see with this topic. And I think it worked. I'm happy with it. I accomplished what I wanted to accomplish. And then kind of something funny happened where halfway through the debate, we just kind of started talking about other stuff. Like, you'll see, we get to the point where, okay, I did what I wanted to do. Great. Now I'm going to address all that other stuff that you brought up, you being Dr. Bergman, that wasn't relevant to the topic, but worth addressing anyway. So this is really kind of like two separate conversations in one. There's the topic of the debate, which, as far as I'm concerned, we settled out like halfway through, and then there's all the other stuff that we talk about. So I'll interject, future Dan, will interject in the middle of the debate when we get to that break point, just so everyone's kind of on the same page in terms of what's going on. So with that said, enjoy. Thanks for watching.
All right. Welcome, everybody, to Standing for Truth. My name is Donnie Badinsky, and I am your host and moderator for tonight's much anticipated debate between Dr. Dan Stern Cardinal and Dr. Jerry Bergman on common descent versus common design. And I got to say, it is a privilege to have these two well-educated gentlemen for tonight's exchange of views. I have seen both Dr. Bergman and Dr. Dan Stern Cardinal engage in debate, and I can say they are both skilled and very well-rounded on these topics. And so for that reason, I can assure you in the audience that this is going to be a solid, professional, thought-provoking, and engaging debate on the topic of origins, and I'm excited. Gentlemen, if we could, let's get acquainted, break the ice a little bit, and get to know you guys before we get into our opening statements. Dr. Dan, let's start with you. Certainly not your first time debating, nor is it your first time on the Standing for Truth debate platform, but tell us, how have you been? And also tell us a little bit about yourself and your channel, Creation Myths.
Thank you. Dr. Bergman, thank you for doing this. It's a pleasure. Very nice to meet you and be able to talk with you. And thanks, Donnie, for hosting. Appreciate the invite. Hi, everybody. My name is Dan. I'm an evolutionary biologist. My PhD is in genetics and microbiology, and my specialty, my work, is on viral genetics and evolution, and coincidentally, very closely related to things like genetic entropy and mutation accumulation is kind of right in my wheelhouse. I currently teach full time at a big university. I have over 900 students, I think, this semester coming up, which starts on Tuesday. So I've been busy getting ready for that. And that's my channel, Creation Myths, is all about creationism and evolution. And I take a really technical look at highly specific creationist claims and go through the science of why they're wrong. And so that's who I am and what I do.
Appreciate it, Dr. Dan. Who needs sleep when you're taking care of 900 kids and engaging in debate on the side? So I appreciate the introduction, helping us to break the ice. For those that want to see more from Dr. Dan Stern Cardinal, maybe you like what you're hearing and you want to see more from him, check out the links, not only in the description box, but also in our live chat. Dr. Jerry Bergman, it's great to have you back here. Certainly not your first time on Standing for Truth, nor is it your first debate either. Couple of experienced debaters here, and I'm excited. So Jerry, tell us a little bit about yourself and tell us a little bit about what you do.
Well, I've taught at the college level for about 42 years, and primarily my area is science, but I also taught in the psychology area, And I was in a medical school teaching and doing research in cancer for several years. I have 3 degrees from a medical school, and I enjoy writing and enjoy learning about evolution. And I was once an evolutionist, by the way, for a number of years. And the evidence convinced me that evolution doesn't have the empirical support. It convinced me that evolution has got a lot of problems, and that's what I focus on. My 2 areas I like to look at are the harm that evolution has done, and there's no shortage of material on this. I have probably 2,000 books that deals with it. And right now I'm doing articles about the harm that evolution has done in Africa, on the colonization of Africa and the belief that the African people were less evolved than the whites. And this is very clear in the literature, very clear what they thought and where they got their ideas from. And I thought I had covered this area pretty well, and somebody introduced me to the fact that, nope, you haven't. You've hardly scratched the surface. You need to look at the evidence for harm that evolution has done in Africa. And I'm kind of overwhelmed by the evidence. I have 4 articles coming out, and several more I'm preparing. So that's my background.
Okay, Dr. Bergman, appreciate that introduction. For those who like what they're hearing from you tonight and they want to see more, they can also check the description box of this video where they can find links to your previous material, as well as your website where you have lots of articles and links to your books. So, gentlemen, appreciate the introductions. Again, this is going to be a thought-provoking, engaging debate. You're both experienced. A couple debates that come to mind. Dr. Dan, you've engaged Casey Luskin in a formal debate. You've had discussions with people like Michael Behe. So certainly not your first rodeo. Dr. Bergman, you've had formal debates with people like Dan Barker and PZ Myers. So I'm excited to see what you're both going to bring to the table for tonight in terms of points and arguments. Again, for anybody joining us in the chat, what are we debating tonight? We're debating common descent or common design. Dr. Dan takes the common descent position. Dr. Jerry Bergman takes common design. And so let's go over our structure, our format briefly. So we are having a formal debate on the topic tonight, starting with 10 minutes each. Dr. Dan will give us his presentation first. Then we'll jump into rebuttals. And so we'll have 6 minutes each where our debaters tonight can engage each other's points and arguments brought up in the opening statements. Then we'll jump into a 40-minute discussion, everybody's favorite part of these debates. We'll break up the 40 minutes into 2 segments. And so we'll have 2 20-minute periods each. And that way you'll both get the opportunity to pick the topics and ask the relevant questions. Then we'll jump right into audience questions. So this is when we get you guys involved in the audience. Please, if you do have a question, let's keep it as much as we can on the topic of common descent versus common design. Tag me either at Donnie or at Standing for Truth, and then let me know who the question is for, Dr. Dan or Dr. Bergman. My goal is to get an equal amount of questions for both debaters for our Q&A period. And also keep it respectful. Our guests tonight have given us their time for this debate. They've given their time to prep for the debate and the debate itself. So let's be professional, respectful, and then we'll wrap things up with a 5-minute concluding statement where our debaters can wrap up their thoughts, wrap up their points, and address anything they feel has been left hanging. Gentlemen, let's get into our opening statements. Dr. Dan, do you want me to get your slides up right away, Dan?
Okay. Yes, let's bring them up right away. And we'll be, there we go. And we got 10 minutes. I got a timer. You have a timer. So you tell me when to go and we're good to go.
You're good to go starting right now.
All right. Hi, everybody. So our debate topic tonight is common descent versus common design. And I'm here to tell you that we already know the answer to this question. It is common descent of all cellular life, not common design. And we're going to talk about exactly how and why we know that's the case. So the first thing I want to just put out there very briefly is, has this question been addressed somewhere that isn't YouTube? Because this is fun, but this is not where scientific questions are answered. So has this been addressed in the scientific literature, in the peer-reviewed literature? The answer is yes. I'll show you two recent examples. So Baum et al. 2016, Statistical Evidence for Common Ancestry, Application to Primates. The authors wrote in this paper, we overwhelmingly rejected both species and family separate ancestry with infinitesimal p-values. And you could go check that paper out. Those p-values are, in fact, very small. And a little bit earlier, White et al. 2013, Beyond Reasonable Doubt, Evolution from DNA Sequences. It's a direct test of this question of common versus separate ancestry. They wrote, quote, it is time that researchers insisted that doubters put up testable alternatives to evolution. So in terms of the peer-reviewed literature, this question is not an open question. The papers are out there. It's been specifically addressed, and I want to emphasize it's been specifically addressed with directly observed data and predictions in the present. Now, if I was Dr. Bergman, if I was arguing against common descent, I would want to refute these papers. But I am not going to use them to make my case tonight. I just want to remind everybody that YouTube is not real life, and the real science is settled on this one. So what I'm going to do is briefly show how we can tell common descent apart from common design, which is to say separate ancestry of the different created kinds. I will not show that only common descent is compatible with the directly observed evidence. I will not do that in this debate tonight because Dr. Bergman is going to do that. He is going to show that only common descent is compatible with the directly observed evidence. Here's how. I'm going to show 4 phylogenetic trees with the names of the taxa removed. So we'll have the tree topologies, the branching patterns. I think 3 out of the 4 show the branch support, the bootstrapping values. All of these trees are based on unconstrained genomic regions, so things like pseudogenes, ERVs, transposons, things that are not subject to purifying selection, things that can freely accumulate mutations. Now, that's not to say these regions are non-functional. That doesn't matter. The only thing that matters for our purposes is that they freely accumulate mutations. 2 of the trees I'm going to show are within something we would agree share common ancestry. They're within a single created kind, and they're narrow enough that I'm confident we would agree once I tell you what they are. And then 2 of them are spanning 2 or more created kinds. They're sufficiently broad that I say they share common ancestry, but I'm very certain that Dr. Bergman says they do not. Here are those 4 phylogenetic trees. And again, I've removed the names of the taxa, but I've left all of the other information as published in the peer-reviewed literature. Now, I'm going to move on because I don't want to just leave these sitting here for the next 6 minutes, but I'll pull these up at any point if Dr. Bergman wants. I can pull them up, whenever. I'll pull these up and we can look at these throughout the debate as necessary. But these are the 4 trees, and again, 2 of them are within a single kind, and 2 of them span more than one created kind, according to the separate ancestry model. Here's how we can test our competing hypotheses. At any point tonight, opening, rebuttal, open discussion, whatever, Dr. Bergman can have me pull those up and he can tell us which ones are which ones are of single kind, which ones are multiple, and how he knows based on separate ancestry with common design. Why am I confident he'll be able to do this? Because common descent and common design make different and opposite predictions regarding what those phylogenetic trees will look like. Those predictions are mutually exclusive. They are not compatible with each other. Only one set of predictions can be correct. So what do we expect based on these 2 competing hypotheses? So within a single kind, we agree, right? If we're looking at something like dogs, right? We agree that all dogs share a common ancestor, I hope. So what we have when we're looking at all the dogs, and when I say dogs, I mean, dogs, wolves, maybe coyotes, whatever, wherever you want to draw the line, right? We agree they share an evolutionary history, so we have a shared pattern of variation within those common ancestors, right? Each node, each branch point represents a common ancestor between the descendant branches. So what we expect to see, what we predict when we construct our phylogenetic trees, is a hierarchical pattern of similarity with strong branch support, that is to say, strong statistical support, and very little polytomy, which is a branch point with more than 2 branches leaving it, or 3 or more, which just means you don't know what the relationship is. So, for example, if we look at a tree like this, right, maybe we've got dogs down here at this rightmost blue branch, and then we have wolves here, and they're more similar to each other than they are to, like, say, coyotes is maybe this kind of purplish indigo branch right here, because those dogs and wolves actually share more of their history together than either of them share in common with the coyote. So we expect this nested hierarchical pattern when things share common ancestry or within a created kind, right? And that's just how phylogenetics works, and we agree on that. We just disagree on where it stops operating. Now, if we have common descent across 2 or more kinds, we expect the same thing, right? My prediction is that when we do the same techniques to 2 or more created kinds, we are going to see basically the same thing, because again, they have a shared evolutionary history. So we have a shared hierarchical pattern of variation in those common ancestors, which means we have the same predictions: hierarchical pattern, strong branch support, little polytomy. So those are my predictions. The common design or separate creation position or hypothesis leads to a different set of predictions, because when you have 2 separate created kinds, they don't share an evolutionary history. There's no shared pattern or no shared history of variation, because all the variation since they got off the ark has developed independently in those 2 groups. Now, mutations are probabilistic rather than deterministic. We know that from direct observation. So the mutations that occur in those 2 unrelated groups will be uncorrelated with each other. So what happens if we were to try to do phylogenetics across created kinds? Well, you take your 2 groups that are unrelated, as I show right here. They don't connect, right? They don't share common ancestry. And you kind of mush them together. And what I'm trying to illustrate here is doing this, right? You have 2 trees and you basically smush them together. And because they don't actually share a common evolutionary history, you're going to get this weird pattern where you don't have strong branch support, right? You don't have high bootstrapping values, and you have lots of polytomy, right? It's just a big jumbled mess. There's no hierarchical pattern of similarity across the kinds, right? So now we have these specific predictions, and they look very different from each other. We could, do this mathematically. You could run the simulations. This is what we expect to see in the case of separate ancestry. Now, importantly, this is true even if the unconstrained sequences were created identical or very similar, or even with a built-in hierarchical pattern across the kinds, because again, all the extant variation has to appear after the arc. So you're going to disrupt or obscure that built-in pattern as mutations accumulate. So we have these specific competing predictions, and this is how science works. You make predictions and you test them. And standing, I see I've got about 30 seconds left. I'm going to run over by maybe 30 seconds or a minute, I think.
No problem.
So we have our common ancestry, nested hierarchies both within and across kinds, common design, nested hierarchies within kinds, but not across them. We can test this with direct observational data. We've made all these phylogenies. The question is, what does the data show? Well, here are the phylogenies. 2 of them are within a kind. 2 of them are across kinds. We should be able to tell which are which if common descent is true, or if common design is true. If common descent is true, they should all follow the same pattern, and we shouldn't be able to tell them apart. So this is just a summary, so let me just go right to the wrap-up. This is how science works. You construct a hypothesis, you make predictions, you test them. Here we have specific predictions. Phylogenies within a single kind will be distinguishable from phylogenies spanning 2 or more kinds according to a common design hypothesis. Is that the case? Let's see. Thank you.
Dr. Dan, thank you very much for that first opening statement. I appreciate the visuals and work put into that opener. To the audience, I appreciate how engaged everybody is already for tonight's great ancestry debate. I am all caught up on the questions that have come in so far. Again, if you do have a question or a challenge for our guest tonight, do your best to tag me at Donnie or at Standing for Truth and let me know who the question's for. Jerry, I will reset the timer. You have somewhere between 10 and 11 minutes, and I will get your slides up here. I'll make sure your mic is unmuted.
Can you see him now?
I do see it. Jerry, if you wanted to, you don't have to, but that little bar at the bottom, you could click hide on it so you're not distracted by that.
Okay.
Okay, you're good to go. Again, Jerry, you got somewhere between 10 and 11 minutes, and I'll start the timer on your first word. Go ahead.
This is the famous progression, which has been used for decades. Now it's pretty clearly rejected by evolutionists. I did a whole article on this. And so nice picture, but it's not based on fact. Here we have the skulls of apes and men, gorilla, Australopithecus, Pithecanthropus, Neanderthals, and Cro-Magnon. Well, the bottom four of those now, the bottom three are now considered nothing more than people groups. By the way, I happen to have a Neanderthal background, and I have some Neanderthal traits, as many others do. And then we have pictures, so many of these, and I have hundreds of them, very human-like bodies and ape heads. And there's a problem with the data, and this is why they have to produce so many human-like bodies and ape-like heads. Okay, what's the source of evolution? Ernst Mayr, ultimately all variation, he says, is due to mutation. Theodosis Dobzhansky said mutation is the only source of the raw material and hence of evolution. So the key is mutations. When I was at the medical school, that was the area I worked in because cancer is a result of mutations. And this discovery, by the way, the discoverer got a Nobel Prize for the discovery that you can speed up mutations by putting fruit flies in an X-ray machine and turning it on. And he got a Nobel Prize because he was able to prove Darwinism, because indeed he found you could speed up evolution. And that was a very exciting development. Now we know, of course, that it's not a good idea to spend too much time in X-ray machines. Nobel lecture of Miller, he said basically, we now know how evolution has occurred by natural selection. Thus, the Darwinian theory becomes implemented. And this was stated in 1946 in his Nobel lecture. Okay, no mutation, no evolution. This is from a book which basically is trying to teach the basics of evolution. No mutation, no evolution. And he brings out correctly, mutations are random, not totally, but to some degree. Beneficial mutations are rare. And diseases are caused by mutations. In fact, a large number, about 5,000 diseases are caused by mutations. Cancer, all inherited diseases, most birth defects. The only other causes are pathogens, diet, and toxins. So basically, an injury, I guess you could add. But basically, mutations are an important cause of disease. And so I did a literature search. This is outdated now, but anyways, those that were labeled beneficial mutations, I found 186 examples, and percent beneficial 0.04. And from these records, I was able to look at most of those that were claimed by the authors to be beneficial. What I found was most were beneficial for not us, but for animals. And this is one example. This is the Ancon sheep example, which Darwin used and has been used in textbooks for decades. And basically, the middle sheep there was born with short legs, and as a result, he didn't jump fences. And Darwin felt, and evolutionists felt since then, that this was a new species. Of course, today that's been rejected. Today we know the Ancon sheep simply is a diseased sheep. Achondroplasia specifically, it is not a new species. Okay, one thing that I learned in doing research on cancer is mutation hotspots. And there are many mutation hotspots, and I have many, many examples. I picked a couple important ones. P53, critically important genetic system, by the way, and this happens to be colon cancer. And you can see that there are 4 areas where are hotspots. The reality here is when mutations occur, they tend to occur in very specific places, at least in many or not, if not most cases. Another example, this is E. coli, and this is an interesting example because the vast majority of mutations occur at number 199, the base pair. And so again, we see another example. And again, I have many more. This right here, hotspots. I did cancer research finding that hotspots had some information on how to treat the cancer. And this is a very hot area now in cancer research because we find where the hotspot is in the gene that was mutated, then we can tailor the treatment to this specific cancer. Now, one issue in cancer research is it is enormously complex. And when one tries to simplify this, it is difficult even to use charts. This is the interactome, and you'll notice there's a lot of yellow lines. These yellow lines are showing, in the case of group A, N, F, F, L, and this protein here is related to quite a few other proteins. Now you'll notice on the one on part B, there's not many lines. Well, that's because we're still working on that. And to draw all these lines to show the interrelationships between the genes has been absolutely horrendously difficult to do because there are so many interrelationships. Why is that important? Because if one gene becomes deficient for some reason, it's mutated, that then affects other genes or other proteins in the biological system. And therefore, it's important to understand these relationships. And in cancer, that is critically important because we want to understand the relationships between the various genes and proteins, and of course, other areas as well, to understand cancer. A lot of people criticize cancer researchers because we take in a lot of money, and so far we, quote, have not been able to cure cancer. Although we've made good progress in certain areas like cancer among children, young children, some of the leukemias. But nonetheless, the reason we have not cured cancer is because the complexities are absolutely enormous. And I should mention the department that I worked in at the medical school, we had 2 deaths when I was there, and both of these people died of cancer. Cancer affects all of us, or will affect all of us. It affects all of us through our relatives, through our friends, etc. And so to say that we're not really trying to cure cancer because we don't want to, because that way our funds would dry up, really is ingenuous because, hey, it affects all of us. It certainly affects people in my family, and I'm sure in many of the listeners, it affects them as well. So we want to cure cancer, but to understand the complexity is absolutely horrendous. With AI and so on, maybe we can understand this better. But that's the interactome, which is the interaction of different parts. This is a drawing which tries to show some of the interactions between the different parts in the genome. And as you can see, it's a mess. Well, they're trying to include all the parts and, well, still have work to do. One thing that I find interesting is that people who accept the evolutionary worldview, this is a worldview, and this is how they see the world, and it's a belief. I do a huge amount of reading. In fact, most of my reading is done in books by evolutionists. And I find that over and over, and I published about 2,000 articles in this area, and I find almost all the research facts that I get are from my reading of evolutionary books. Well, why don't they understand that their own research is not able to prove evolution? Well, often they say, well, this is the state of the research. We found thus and so. We found there's, for example, insects. We found no good evidence for the evolution of insects, in spite of an enormous amount of evidence, especially, of course, amber. And various reasons are given why we don't have the evidence. And the author believes evolution occurs and basically says, well, in time, we will find more and more fossil evidence. And in time, we will find more and more evidence of the evolution of insects. And therefore, they believe it, even though the evidence does not show that. And so when I do my research, I basically find what did they find, or I look for what did they find, and then I can summarize the literature. And most of my articles basically are summary of the peer-reviewed literature written by evolutionists. And then I can summarize it, and basically they got the information. So certainly that's not the problem. The problem is they believe in evolution. They, as is said, they see the world through evolutionary glasses. And when you see the world in this way, yes, it's going to be hard to see the world without those glasses. Okay, another example is that one of my first areas of interest, in fact, this is one of the main things that
1 minute left.
That converted me from evolution to the creation worldview was the fact that there was, when I was younger, 100 organs claimed to be vestigial. And in doing research in the literature, I found that all of them were found not to be vestigial or not useful, but all of them were very, very useful. And so now we basically gone from 100 to none. And by the way, my book in this area has been published in a number of languages, including Arabic. And here is a tape that I did. Vestigial organs from 100 to none. Indeed, all of them have a function. In teaching anatomy for many years, I always checked the index for vestigial. It wasn't in there. The word was not in there. And I checked the appendix. What do they say? Well, for all these organs, they say they have a very important function, or at least a function. And therefore, the anatomy professors recognize that indeed there are no vestigial organs. Biology, on the other hand, most of the biology textbooks that I use claim there were a number of vestigial organs. And that surprises me. It seems the biologists don't know their anatomy that well. So
10 seconds left.
Okay, to stop.
Okay, Jerry, thank you very much for that roughly 10-minute opening statement. Gentlemen, Dr. Dan, Dr. Bergman, that wraps up our opening statements. Again, thank you for the slides, the visuals, and the work you both put into those. And okay, we're moving into our rebuttal. This is a rebuttal of 6 minutes where we can now interact and engage with each other's arguments and opening statements. And so I will reset the timer. Dr. Dan, you have 6 minutes. Go ahead.
Thank you. Just set my own timer here. Okay.
Sure.
So, that was, I want to make sure my sound is okay. Great. So that was a whole lot about what is wrong with evolution. Not much of it relevant to tonight's topic, so I'm not going to get into most of it. So our debate tonight, common ancestry versus common design, or I guess I should say common descent versus common design, hypothesis A versus hypothesis B. The way we test hypotheses is we make predictions. I've heard Donnie say a million times, that's the gold standard of science, is making predictions. And then, of course, you have to test them and have accurate predictions is really what we want to see. So that's what we can actually do here with regard to this specific topic. Some of what Dr. Bergman said would be great for a debate on genetic entropy, for example. It would still be wrong, but it would be more relevant. But he did say a really important thing that we agree on, and I always like to highlight where we agree, and that is on the point that mutations are mostly random. The word I like to use is probabilistic. This is great because this means we should agree on what the competing predictions are for our respective hypotheses. So one thing, I'll throw this out there now and I'll ask directly later, but I just want to confirm that I hope is the case, that Dr. Bergman agrees with my presentation of the competing predictions of what we each expect to see in our respective models. Now, that should be the case because if we start with two identical sequences, just hypothetically, you have two identical sequences that are separately created, right? And then we let each one of those sequences, right, it has descendants and mutations, and each one is going to randomly accumulate mutations in their separate independent groups. The mutations that occur in each of those groups will be uncorrelated with each other, because even when you have things like hotspots, that doesn't tell you what specific mutations will happen. The consequence of this is that on the flip side of that, within each group, they're going to follow a predictable pattern of that nested pattern of similarity. So if common design is true, which is to say, if separate ancestry is true, then Dr. Bergman must be able to tell a phylogenetic tree that includes a single kind apart from one that spans two or more kinds. And Donnie, can you please put up the slide that I have up right now with those 4 trees again, just so everybody can see it? Because again, I'm very confident when I picked the clades to show here that 2 of these are extremely narrow groups that everybody here agrees shares a common ancestor, and 2 of them are very broad groups that I say shares a common ancestor, and I'm very confident that Dr. Bergman would say does not share a common ancestor. Now, given that, and the fact that the mutations are probabilistic, which we agree on, for the phylogenies that show a single created kind, we should see a time-dependent pattern of similarity as the descendants of the arc kind diversified following the flood. Across 2 or more kinds, that pattern of mutations in those different groups is going to be uncorrelated, so you should see lots of polytomy and very weak branch support. So again, I just want to emphasize this is the key thing. According to the separate ancestry, the common design hypothesis, it should be easy to be able to quantitatively and qualitatively tell these phylogenies apart, tell us which one is which. And I've seen probably 20 times in the chat, lines on paper don't prove anything. And I think you all are missing my point, because I'm not saying that anything I'm showing proves the common ancestry of any of these groups. I'm saying that if we assume that very narrow groups share common ancestry and very broad groups don't, we should be able to tell them apart based on the pattern of mutation accumulation since they descended from their common ancestors. And when we compare within a single group, that's going to look one way. When we compare across multiple groups, that's going to look a different way. And I have 1 minute left, and I'll explain why this is the case very briefly. There's this technique that you do to check your confidence levels called bootstrapping, where you look at your data and you take a subset of the data and you compare just using that subset. And the bootstrapping value is the fraction of the time you get the same branching point or the same pattern in your tree. And if you have 2 separate groups that don't, in actuality, share a common ancestry, the presence or absence of one mutation in one of them will be uncorrelated with the presence or absence of another mutation in the other group. So when you start doing these subsamples, you're going to very rapidly get different branching patterns depending on which subsets of the data you use. That's why the branch support and the presence or absence of the multi-way branch points, the polytomy, matters so much. So again, the point here, the gold standard of science is competing predictions. Here we are. Which prediction does this data fulfill? That's the question. 5 seconds.
Thank you. Appreciate that, Dan. It's as if you've debated before. So appreciate the timing there. And okay, that is Dan's 5 or 6 minute rebuttal. Jerry, we're now going to reset the timer and hand it over to you. You also have 6 minutes for a rebuttal starting now. Go ahead.
Okay, thank you. It's interesting that creationists love these phylogenetic trees. Todd Woods has done dozens, many dozens of these. And I have to admit, I'm critical of both creationists and of evolutionists when they use these. I find there are major problems with them. And I pointed that out, not only the evolutionists, but also the creationists. And there are a number of problems. Number one, judgments are made relative to where people are, what genes you use to make the tree, what structures you use to make the tree, and so on. And you can select the structures you want, certain structures, and get a certain tree. You can select other structures and get another tree. And so I have to admit, when I look at these phylogenetic trees, I'm right away very skeptical, and I don't put a lot of weight into them. I brought out that mutations, 99% of all mutations are repaired. That's the estimate. And so you're not looking at mutations, you're looking at those that are repaired incorrectly or are not repaired. And as a result, in doing the cancer research, it's clear to me, since the vast majority of mutations are not going to produce any genetic variety, what they're going to produce basically is deterioration of the genome. And of course, that's what happens in cancer. The genome deteriorates, genes don't work, and as a result, they're broken. We say they're broken, and as a result, you have the genes that speed up the cell division and genes that slow down or control the cell division are not working properly, and that's what causes cancer, basically, very, very simplified. The proto-oncogenes, the oncogenes, and of course the tumor suppressor genes are the genes that are critically important. And what we find in looking at them and other genes is that you don't see much evidence for improvement, as I pointed out when I looked at the literature on mutations. What you see is pretty consistently deterioration of the genome. So it goes down as far as functionality. And therefore, you don't have the luxury of basically producing new variety, or at least it's limited, because most of the damage basically causes the genome to be less effective or the genes to be less effective. And that's why you end up with disease. That's why you end up with cancer. Things don't work. And so I'm skeptical of, especially when I work in the area of cancer research, you can see that the overwhelming majority is deterioration. And you see this very, very clearly, especially certain genes being broken down, the control genes that control cell division. And that's very important in understanding that you're not going to get improvement, you're not going to get evolution, you're going to get de-evolution. And that's, of course, what we see around us. That's why the number of genetic caused diseases is going up. And I know when that's at the medical school, people used to say, well, you're going to cure cancer and you'll be without a job. We don't have to worry about that, because new diseases caused by mutations, by genetic deterioration, pop up, it seems like, one or two every year, or at least we become aware of one or two every year. And so we have plenty of work to do, and I don't think in my lifetime we're going to be able to deal with all that we have to do in dealing with cancer. So indeed, one of the major reasons I dropped evolution was when I worked in genetics at the medical school, you could just see it's not going to work. You're not going to get improvement. You're not going to get changes that by and large would be beneficial. You'll get by and large information, deterioration, and deterioration of the genome. Although occasionally we get a gene that's broken, doesn't work, that allows other genes to occur. And so therefore that is not really common, but there are a number of cases where damage to one gene allows the expression of other genes. And so that's why we assume that they were mutating and therefore producing improvement, but they don't produce improvement, they just produce allowing another gene to be able to express itself, especially in coloration. There are various areas like that. And so indeed, as I thought about this over and over at the medical school, and there's no way that evolution could occur, since we have no good evidence for the origin of new genetic information. The whole idea of evolution fails, and therefore these phylogenetic trees are useful, are interesting, and I know creationists love these. They've got lots of these trees that they work on as well, and I'm skeptical of whoever does them. I just don't think that you're going to make any progress by looking at these trees. By the way, I had a hypothesis not too long ago that indeed there should be evidence for the evolution of the tongue. We all have the tongue, it's necessary to talk. Fish don't have tongues, so therefore there should be evidence indeed from a tongueless animal like fish to a tongue animal like humans and I guess all primates.
1 minute left.
And so what I found was very clearly in the literature, there's simply no evidence at all that we move from a tongueless creature, a fish. Fish don't need tongues, they open their mouths and swim forward, to a tongue. And of course, without a tongue, it'd be pretty hard for mammals, in fact, for many animals to survive. And so therefore, indeed, the literature pointed out, supported my position, and therefore my hypothesis was shown to be correct. And that article hasn't come out yet, but it will shortly. And,
Jerry, thank you very much for that 6-minute rebuttal. Gentlemen, that concludes our opening statements and our rebuttals on tonight's debate on common design versus common descent. Gentlemen, we're now moving into an open discussion where we can directly engage each other in regards to the points and arguments brought up so far. And what I want to do is break it up into two sections, 20 minutes each, because I want you both to have equal amount of opportunity to ask the questions you'd like to ask and also discuss the topics you'd like to discuss. And so Jerry just ended with his rebuttal. Therefore, Dan, let's give you the first 20 minutes to lead the way in discussion. Go ahead.
Okay, so a couple quick things I want to address, then I'll kind of bring this back to the main thing. So it's true that, you know, when you do phylogenetics, you're always making judgments on what to include or exclude. And it's true that you have varying levels of confidence, and, you know, creationists don't have to accept like the validity of phylogenetics. None of that matters for the argument I'm making. It's just that within a kind versus across multiple kinds, the phylogenetic tree should look different, right? That's the only argument I'm making. In fact, I think creationists would like what I'm saying tonight compared to what I'm usually saying, because what I'm showing is based on the assumption that you have separately created kinds. And we're saying, what is that? What can we predict from that assumption? So you can pick any gene, any region. Ideally, you would make it similar, and the trees that I showed are similar things across all those genomes. Mutations produce, you know, deterioration. We don't see evidence of improvement. None of that. That's not relevant. It doesn't matter. No new genetic information. Jerry's welcome to quantify information and explain how we can say that there's no new information. If he wants, we could do that. But the thing that I want to clarify, and kind of where I want to throw to Jerry here is, I want to start. By the way, I apologize. I should be calling you Dr. Bergman. What should I call you, Jerry or Dr. Bergman?
And Jerry's fine.
Jerry, thank you. All right.
That's what people who like me call me.
So, what I want to first make sure is that we agree on the predictions that the two competing hypotheses make, right? So we've got, I say all cellular life shares common ancestry. You say within limited groups, you have common ancestry, but each group is separately created or separately designed. So then the predictions, because the mutations are approximately random, then we should see uncorrelated mutations that occur in those different groups. Let's start there. Can we agree on that like in this lineage and that lineage separately created, those mutations should happen independently and uncorrelated from each other? Can we agree on that?
That seems reasonable. Yeah.
Okay, cool. So now we have agreement on mutations are going to be independent across our different lineages. What happens when you do phylogenetics with two groups that don't actually share common ancestry, you get this like gibberish. You get a tree where it's very low confidence, and you get a lot of situations where you can't actually determine what the pattern of relationship is. The reason for that is you're going to have instances where you have convergence, where the same mutation has occurred. You're going to have different mutations. The mutations that are linked together in the different lineages are going to be different from each other because, again, they're uncorrelated and probabilistic. So when you do phylogenetics across two separate groups that in reality don't share common ancestry, the phylogenetic tree you get is a mess. It's gibberish. It has low bootstrap values, which is to say low confidence in the various branch points. And when you sample different parts of those same genomes and do the comparison again, you get very different trees. Now, under common ancestry, across those same groups, if you say they share a common ancestry and you predict what you should find, you should clean up a lot of that messiness. You get much higher branch support, and you should have less polytomy. And when you compare across different parts of the genome, those trees should be more consistent with each other. I know that was a lot, but can we generally agree on those differences in the predictions between common ancestry versus common design for things that are separate in the creation model?
That sounds reasonable. Yeah.
Okay, so we can look at a phylogenetic tree, and like they're very different from each other, both quantitatively in terms of if you do the math and calculate the bootstrap values, and also in terms of just the branching pattern and the pattern of the hierarchical organization. So, Standing, if you would be so kind, then if you could just, I'm going to put my screen every time I move out of the PowerPoint window, it vanishes. But I'm just going to put this up right here. So here we have our trees, and I will tell you that two of them are for rodents. One is, I think, one is mice and rats, and one I think also includes gerbils. And then two of them one of them is all simians, and another is all primates, which I think I think you would agree in the creation model that all simians and all primates constitute more than a single created kind. It's two or more groups in there. Whereas like rats and mice, I hope I was okay in assuming that we would agree that's a single created kind. I hope that was an okay assumption. But I've kind of pulled back the curtain a little bit on this in terms of what the groups are that we're looking at, even though I haven't said which is which. The thing is, because we agree that mutations are probabilistic, and we agree on the consequences of that reality in terms of the structure of phylogenies when you're comparing across created kinds compared to within, with the separate ancestry model, the common design model, we should be able to tell which of these two trees is which. Can we do that?
Yeah, A and B are similar. B and C are similar. And B and C look like you would say they don't have common ancestry. A and B do have common ancestry.
A and B have common ancestry. So I actually have to pull up my
answer. No, A and C, sorry. A and C have common ancestry. B and D do not. Sorry. You get along great with some of my creationist friends. They talk about this. They say the same things. They talk about this endlessly. So they agree fully with you.
Okay, so you're saying A and you said A and C share common ancestry?
Share a common ancestry.
A is a single kind, and C is a single kind. That was what we're
right.
Okay, A is a single kind,
and B and D do not.
Am I right? I'm just checking my answer key here. Okay, so before I give you the answers, I'm going to tell you if you're right or wrong. Why? What's the rationale here? What's in terms of the shape of the trees, the branching? What's the rationale?
Because for A and C, you can look at the single common ancestor right at the top, and all the others descend from that single common ancestor. Mm-hmm. Where B and D, you have several different, it looks like, although you actually could argue B that at the top line, that's a common ancestor for all of them. And D, you could argue that D, the top line, is common.
I'll just tell you, for the paper for D, they, for whatever reason, 99% of the time when you see these, they draw in what's called the root, right? That last little vertical branch in there. So you can see that in A and in C and in B, they drew in the root on the tree. And for whatever reason in D, the authors just didn't draw the root, but that's there should be a root. Like I would have drawn a root there. So you do actually have a common ancestor here indicated on the tree as well. Yeah. Now, the thing is, according to your model, two of those common ancestors are real and two of them are not. And we just agreed we should be able to tell them apart, right?
My creationist friends could, but I guess I can't. Sorry.
Okay.
But my creationist friends probably are more attuned to this than they could.
Okay. Folks, that is my point. That is the whole point right there. We have very specific predictions because I think we can all agree that these trees all look pretty similar to each other, right? We have a common ancestor. We have a few branches on these are weak support. You've got weak branch support for this individual clade right here, fairly weak branch support down here. But if you look through these trees, you get reasonably strong branch support. For this one, it's color-coded rather than showing the numbers, and in the figure legend, it tells you what the colors mean, but it's robust branch support across all of them. And what we don't see in these trees is examples of polytomy, right, where you have 3 branches or 4 branches or many branches coming out of the same node. When you have polytomy, that means we don't know what the relationship is. And polytomy would be indicative of a comparison across created kinds, because that means when we sampled different subsets of our data, we got different answers. And that's what we would expect to see if they were separately created, accumulating mutations separately and independently from each other. The fact that we don't see polytomy on these trees indicates that they do, in actuality, all share common ancestors, top to bottom across all of these trees. Right? And it's not me that's saying that this has to be the case. We agreed on what the predictions are. We agreed on the various predictions of the 2 models, right? We agreed that mutations are probabilistic, and therefore that leads to different expectations, which is to say predictions, when you compare within a single kind versus when you make a phylogeny across multiple kinds. And we know, we have real world examples of this, because we know that we do have biological entities that don't share common ancestry. It's the viruses. Viruses, folks, are polyphyletic. That is to say, viruses have multiple independent origins. And when you make a phylogeny, when you attempt to make a phylogeny of viruses across different groups of viruses, this is not a real example, but it's a made-up example. But if you were to compare across like the pox viruses and the Gemini viruses, you would get this kind of thing. You would get some nonsense like this, right? So we know what it looks like. Okay, so I'm gonna put this aside, and I'm gonna address, because we accomplished what I wanted to show there. So I'm gonna put this aside, and I want to just ask Dr. Bergman about a couple of the things he said in his rebuttal, because I think I made the point I wanted to make there. So let's talk about information.
Yeah, possibly.
Okay, future Dan here. Just want to jump in and say this is the point where we're going to change gears, and the rest of this conversation is only going to be about whatever random stuff Dr. Bergman is bringing up. And I think I'm able to address all of it. It's all the kind of usual creationist arguments that you hear. There's nothing new here. And I think it is worth addressing. And I will periodically kind of check back in with the original topic and be like, hey, by the way, we settled that one. Thank you. While we talk about this other stuff. So enjoy the rest of this, enjoy the Q&A, and once again, thank you for watching.
If you guys think it's okay, before you get into those questions, did we want to give Jerry just an opportunity to maybe sum up his thoughts on that specific segment, on the phylogenies and the specific predictions, before we move into another topic? Jerry, if you had anything to add to that, or we can move into...
Yeah, I could mention the basis of evolution is 2 basic ideas. One is natural selection, and the other is the origin of biological information through, now it's understood to be, mutations. Darwin didn't, of course, realize that. He thought there would just be an infinite variety in life. So now it's the mutation idea has become dominant probably since the 1920s or 30s. So anyway, so it's the 2 basic ideas. And natural selection, that's not been a problem. That's pretty obvious. You're more fit, you're more likely to survive. Natural selection, though, is really important because it reduces the degeneration of the genome. So as the genome degenerates, it reduces the genome degeneration. So natural selection works in the favor of our worldview, of my worldview. On the other hand, if you have no source of biological information, you have no source of new biological information, evolution fails. And Darwin had no source. Of course, he just assumed that there's infinite variety when he bred pigeons and so on. He thought, well, gee, we've got a very different organism, looks very different at least. When we breed pigeons, we get very strange, non-pigeon-like creatures. Well, now we know, of course, there are very limits to breeding. It only goes so far. We know that in horses, if you can breed a horse that's 1-2% faster, you can become very, very rich. And so we've tried to breed as far as we can, and there is in every case limits that we can go to. Maybe we can go slightly beyond that, but by and large, there are clear limits that you can go in breeding. Of course, Darwin didn't realize that. And so you have to have a source of new biological information in order for evolution to work. Once you don't have that, and we don't have that, and that's very clear from the research, therefore, evolution fails. And therefore, all the other arguments need to be explained, of course, but it can't be explained by evolution. My creationist friends claim all the phylogenetic trees proves creation, and I know I've gone through circles with them, and that I don't think it does, and they think it does, and so on. And I point out the flaws in their phylogenetic trees, and they say, well, yeah, you got a good point there, but on the other hand, it still proves creation. So they use it to prove the different story than Dan does, but they both are very involved and very knowledgeable. Both, well, Dan and my friends are very knowledgeable about these phylogenetic trees. But I guess I have to admit I'm skeptical, because you have to have a source of new biological information, a viable source, significant biological information, and you don't have that. We know that interbreeding and so on, you can get variations, but this is not, as I know, it's rarely new information.
Okay, let's put a pause there. Jerry, appreciate those points. Dan, those are probably some of the points you want to engage anyway, so let's throw it right back to you. Go ahead, lead the way.
So first thing I want to point out for everybody is, as far as the predictions from our two competing hypotheses go, we agree on what those different sets of predictions are, and we just showed directly that the directly observed data are consistent with the predictions for common descent, and they are in conflict. The data are in conflict with the predictions from common design. So as far as I'm concerned, we're good. We're good, because now the case that Dr. Bergman is making is that you can't have what we might call macro evolution, because you don't have a source of information and you need new information. So there's two things I want to just kind of zoom in on here. First is that we both agree that you can get new information, and I'd be happy to demonstrate why that's the case. But before I do that, because I want to make sure we're on the same page here, how are we when we say there's no new information through evolution, how are we quantifying that? How are we defining information, and how are we showing that it's not increasing?
Well, that's of course a good point, but my point is that we don't not only get new information, significant new information, we get degeneration. And when I was at the medical school, I mentioned some of these things, like, what about beneficial mutations? What about new information? And I learned not to bring these things up, because I got the look. You know what the look means? The look means, what are you talking about? Mutations are invariably harmful. Beneficial mutations, what are you talking about? We're talking about reality. We're talking about
Jerry,
yeah, okay. Yeah, let me okay. So, but the question was, how are you in order to claim you don't get new information, we need to be able to quantify information in a genome. How do we do that?
Are you basically asking, Dan, and just to reiterate, just so the audience is on the same page, how do we quantify the idea of new information's been added, information's been lost?
Yeah, like
how can we understand that?
If I showed Dr. Bergman genome A, genome B, complete sequences, how can we quantify which of those two genomes has more information in it?
Go ahead, Jerry.
Probably of course, you could look at the number of genes involved, a number of base pairs, I suppose, and there'd be a number of ways of quantifying it, but I agree that's to some degree problematic. But what you're looking at is, you have two genes that are very different. How did you get that gene that's very different? One could assume that, well, that gene that's very different started out looking like a gene that's very similar, and slow changes caused gene A to become gene B. These slow changes were small changes, and therefore you have new information because of these small changes that occurred in gene A, and which brought us to gene B. The problem is, though, that's so few cases. When we're talking about genetic differences, we're talking about huge number of differences. We're talking about, now that's true, many genes are similar, yeah, I know that. But on the other hand, there are a large number of genes that are very, very different in the human.
Can I yeah, so with respect, Dr. Bergman, that's a separate question, though. The question specifically is with regard to information, but you did say that maybe if one genome is longer than the other or has more genes than the other, those are two ways we might quantify the information. So in terms of length, I mean, genome duplication or gene or whole genome duplications are things that are directly observed. So by that metric, that's increasing information. If we use genome size, which there's a case to be made that that's a valid measure, and there's a case to be made that it's not. But if we do, that's really easy to get new information. New genes is another good one, right? So if you have a new gene, well, we get a long list of new genes that we agree are new genes because they exist within a single created kind, but they're orphan genes within a single lineage within that kind, right? So if we have a new gene within a single lineage, within a group of organisms that we agree shares common ancestry, then we should both be able to agree that that is a new gene that appeared within that lineage since the ancestor or the ancestors that lineage got off the ark 4,400 years ago, give or take. And there's a lot of examples of that we can look at. So you've got the famous antifreeze protein in the Arctic fish. You've got nyelinase. You have, chimpanzee. I don't know if you consider chimps and gorillas the same kind or a different kind. I know there's debate about that. I don't know where you fall down on that. But if you look just across the great apes, each different group of great apes has genes that are unique to that lineage, which means if you're going to say that new genes, which is to say new information, can't evolve, now we're going towards species level creation rather than, kind or family level, wherever you want to approximate that kind of level, which I don't know your specific position on that, but most creationists kind of consider that a non-starter because of the issues that go along with having each species individually created. So by any of the standards that we're describing here, right? And I've had other creationists tell me you can't quantify information, but you gave two metrics. By either metric, we can generate new information. And then right at the end there, you kind of alluded to a waiting time problem thing. And that's, I've personally done the math on that. And it's not complicated to get, for example, from a common ancestor of humans and chimps to humans and chimps, all the differences that need to accumulate based on directly observed rates of mutation accumulation and recombination. I've actually directly done the math on that one. So I think that's about my 20 minutes for my half of this. I think I addressed those objections. Thank you.
Okay, thank you, Dan, for that first 20 minutes in terms of our discussion here. Jerry, feel free during your 20-minute back and forth where you now get to lead the way in discussion, bringing up the topics you'd like to bring up. Correct me if I'm wrong, Dr. Dan, you brought up a couple points there in terms of nylon digestion, orphan genes, notothenoid, antifreeze, Arctic fish. So if we do get in, continue in the world of genetics and mutations, we could perhaps engage those. Jerry, up to you. You get 20 minutes to now lead the way. I will reset the timer. And
okay, these examples, minor changes are certainly possible. The nylon, of course, example, I think it's rather simple change that cause an enzyme to be able to break down a similar protein in that case. And that's true with many of the other claims. My concern is, partially relating back to my background in the medical field, is that overwhelmingly genomic changes deteriorate the genome. You have some near-neutral mutations, a lot of near-neutral mutations. Near-neutral mutations are not a problem individually, but they add up. And near-neutral mutations, they add up, then they end up with genetic catastrophe. And a good example is aging. As we age, we end up with more and more mutations, more and more new mutations, and therefore more and more non-lethal mutations, more neutral mutations that add up and cause a problem. A good example of that is when my aunt died. She was a person that, I guess the only time she went to the hospital was when she delivered her only son. And I asked the doctor what she died of. And the doctor said, well, she didn't die of anything. And I said, wait a minute, she died of something. And the death certificate said myocardial infarction. She must have died of something. So he said, well, Bergman, sit down. She actually died of everything. She was 90 something. Her lungs were not as good. Her kidneys were not as good. Her veins were not as good. She was suffering from degeneration of just about every organ in her body. And what happened was not that one organ failed, but that they all failed. And the end result was the heart failed. And as a result, she died. And so this would be, we were surprised because the woman, as far as I know, never had any illness or major illness in her life. So she died as a result of the accumulation of a lot of near neutral mutations, which eventually ended up to genetic catastrophe. And you get the same thing in species. Species go extinct because of that problem. And you get the same thing in disease. And of course, you get the same thing in the longevity of people, et cetera. And so that is the trend we see that is dominant in the natural world. And therefore, that goes against evolution. And basically, when you talk about evolution, you're talking about going the other way. You're talking about new genes, new information. And yeah, you can get minor genetic duplication. I know you can, and you have, in a sense, new information. So you have some mechanisms that will produce new information. But as a whole, what's going to happen is you're going to end up with deterioration of the genome, and you're going to end up in time with the death of the person and the species. Now, we're very aware of this in medicine. It's a clear concern. And the concern is that indeed we have deterioration of the genome, and therefore we have to come up with medical ways of being able to deal with this. And so we're very cognizant of this fact, and we look at it as basically a challenge for medicine. That when we deal with one disease, and we've actually dealt effectively with many diseases, but nonetheless, you are going to have other diseases in the near future that we have to work with as well. So we're not going to end up with the end of disease. We're going to end up with the end of a lot of diseases, but in the future, we are going to end up with new diseases or new medical problems because of the accumulation of mutations. And that's, I guess, in medicine, we focus on that. And therefore, it's hard for me to understand how we could produce a scenario which we start out with amoeba and end up with people. That just is not viable when you look at the reality of genetic world and the reality of genetic deterioration. And therefore, by the way, why isn't this more commonly talked about? The reason it is not more commonly talked about it is Dan has the privilege. He can present his information with his 900 students, no problem. But if a creationist would present some of the information that I did, I had to be very careful presenting this information relative to genetic mutation. If a creationist presented this information, he or she could get into trouble. And that's why I've written 5 books, which cover about 200 cases of people who question, and some of these were evolutionists, but they just questioned the ultimate, I guess, goal. Michael Behe is, I'm thinking, he's an evolutionist, and yet he still has certain questions about the evolutionary mechanism. And so we're going to end up without a job or without a career. And
Dr. Bergman?
Work with, go ahead.
No, I appreciate that response. A few points there. So what we'll do is, Dr. Dan, let's hand it back to you now, and feel free to engage whatever points there you'd like to, and we'll go back and forth in a free-flowing manner that way. Go ahead.
Thank you. So a couple things I want to just highlight here. First, just want to remind everybody that we're now kind of talking about a different topic, right? We're talking about kind of evolution writ large rather than just the more narrow question that we started with of common descent versus common design. And with that question, again, in terms of how we settle scientific questions, it's about competing hypotheses and competing predictions. We did that, and the predictions of common design were wrong. Dr. Bergman helped show that with the phylogenies. So now we're talking about the ability to get new information or the inability to get new information, the trajectory of evolution, and kind of the second order argument that if you can't get new information, or if evolution is necessarily reductive or destructive, then you can't have macro evolution, if I could use a word that Dr. Bergman didn't use, then that precludes common ancestry of all cellular life. So first, I just want to point out for everyone, I hope you all noticed that Dr. Bergman agreed with me that we can increase information. We went from no information increase to we can increase information, but it's small scale, it's limited. You can get new genes maybe, but not larger scale stuff. So I appreciate that we at least agree on that narrow issue, that you can increase information in the form of like new genes, for example. Then getting into the kind of the bulk of that was mutation accumulation, genetic catastrophe was the phrase that Jerry used, which, the word that I know for that is error catastrophe, which creationists often use the phrase genetic entropy to describe that. And Jerry used language that was very similar to what Dr. Sanford used in his book and in his presentations on genetic entropy. Now, I love when this topic comes up. I know it's not strictly the thing that we came here to talk about, but let me tell you, this is one of my favorite topics. This was actually something I worked on in graduate school. You could read chapter 4 of my dissertation. It's all about my attempts to induce error catastrophe in single-stranded DNA bacteriophages. This is my thing. And even more conveniently, last year, I was a co-author on a paper on genetic entropy with my friend, Dr. Zach Hancock. And we showed that the math that Dr. Sanford uses, that Dr. Bergman just described very closely in terms of the accumulation of nearly neutral, slightly deleterious mutations, we showed that the math that Sanford uses to reach that conclusion is wrong. We actually empirically showed, using empirically determined distributions of fitness effects and mutation frequencies, we showed that that's not actually what happens, and that's in line with other studies that have been done on this in model organisms where you mutagenize them, predict that they would go extinct due to error catastrophe, and instead what happens is you see a widening of the range of fitness in that population. Many of them are very low fitness when the mutations accumulate, but you do generate high fitness genotypes as well, and the population just ticks right onwards with no problems. We also tested this in the Lenski long-term evolution experiment with the mutator lineage, which according to this hypothesis, this kind of version of population genetics, that lineage should have gone extinct, but instead that mutator lineage was one of the highest fitness lineages in that experiment. And just the very last thing, and then I'll send it back, just on creationists not being able to present this stuff. This is kind of a hobby horse of mine, Dr. Bergman. I think you should, submit an abstract to a conference, do a talk, do a poster. I guarantee you, they would love to have something like this in there because conference promoters, you know what they love? Controversy. And if you have creationists coming to conferences, like I know that I'm very confident if you were to say here's the population genetics of genetic catastrophe and wanted to present that, people would want to hear it and look into it and critique it and whatnot. You would not be barred from that. I think that's something all creationists should do. I think you should all be, getting your foot in the door. Come on into the conferences. It'd be great. I would love to see creationist posters at evolution conferences and talks. Back to you.
Go ahead, Jerry. Feel free to engage any of those points or comments that Dr. Dan brought forth. Go ahead.
Okay, yeah, that's interesting that the 200 cases, and I have 3 forward drive file cabinets full of documentation. Dr. Dan, if everybody was as open as you are, this would be a much better world, to be honest. But the intolerance is enormous, and I can give you many examples of a tenured professor who has her graduate work, her postgraduate work at Harvard University, and she did comparisons between the genes of prokaryotes and eukaryotes, and she found there's no way that prokaryotes could evolve into eukaryotes. The genetic difference was enormous, and she was fired, lost her job. And as far as I know, she hasn't been able to find work since. And that is typical of what happens. And they could not. I've got the hearings that she had. She did have hearings at the university. I think it was Missouri State University. And she had hearings there, and I got a copy of the transcript, read through the whole thing, and 600 and some odd pages, I guess it was. And indeed, they could not find anything wrong with her presentation, anything wrong with her data, anything wrong with her conclusions, nothing wrong. What they got her on is that she had published in non-approved publications. They had a list of publications that were approved at her university, and her publications were not in this list of approved publications, and so they terminated her on those grounds. And as a result, she's unemployed. And this is over and over. Now, there were a few very tolerant people on her committee that basically said, this is wrong what we've done. We have done this in the past with other people who ended up with Nobel Prizes. We let them go. Specifically, the woman who discovered the research on jumping genes. And she was employed there, but didn't last long. And she, of course, won the Nobel Prize for her work on jumping genes. And so they mentioned this, that we've done this in the past, and we're doing this again. Unfortunately, though, she was in the minority, and the faculty voted basically to terminate her 10-year contract, and they did, and now she is without a job. And so you see this over and over. And again, I've got 3 file cabinets, 4 drawers each, full of documentation of what goes on. So these debates we're having, we can have them on, thanks to Donnie, we can have them here, but can we have these debates at a university? And so many times, now maybe at Dan, your school, we can, but so many universities, you cannot have these debates. They do not want to hear the other side, and they're very adamant that indeed only one side will be presented. Dan, you saw my slides. If I presented that at your university, do you think I would survive? Now, you would probably say, oh, no problem. But on the other hand, I have a feeling that if I presented these slides at your university, if some of the evolutionists were aware of them, I might not survive. And when I was teaching at the college where I taught, I had to be very careful that I was very tactful in not hinting against evolutionary theory, but I was presenting information which we need to look at. And so I survived 42 years.
Jerry,
but I was very
I can answer that directly. That last thing, I'll just real quick, I'll address that directly. So you would not be able to come into a classroom and teach young Earth creationism because it is not a well-established, well-supported scientific theory, right? And in science, theory is the highest level of confidence we have. But creationists would not be barred from publishing papers, arguing for their ideas, and coming to conferences and making their cases. That's where you push open the door. And then once you become established, then you get into the classroom. The classroom is where we do the boring stuff that everybody agrees on, right? It's in the literature and in the conferences where you can throw new ideas out there. And I can prove to everybody here that creationists are not censored for putting their work in the peer-reviewed literature, because off the top of my head, while you were talking, I came up with a list of creationists who have published legit peer-reviewed papers in the peer-reviewed literature in the last 20 or so years. I mean, you've got Douglas Axe, Michael Behe, Sanford, Beckley, Basner, Hofstra, Cordova. And then in terms of having dissenting opinions and people who are making very similar arguments but are not explicitly creationists, you've got Dennis Noble, and you've got all of the extended evolutionary synthesis people, all of the third way of evolution people who are making essentially critiques of evolution that would not be out of place on the pages of like Creation Ministries International, for example. And so we know that these ideas are not prohibited from the literature, but where, look at, for example, Nathaniel Jeanson or Georgia Purdom or Rob Carter, or, the list goes on. Any of these, PhD creationists, where do they publish? They publish in the Journal of Creation. They publish in Answers Research Journal. They publish in Biocomplexity rather than the actual peer-reviewed literature. And the only people stopping them from doing that are the creationist authors themselves. We know they can get their papers published because they have, and they do. And like every time I see, Bill Basner or Ola Hofstra's name on a paper, I'm like, oh, I'm going to deal with this creationist in the literature, right? So some of them are actually doing it, but most are not. And that's not evolutionists keeping anybody out. That's creationists just not trying. But there's no barrier to, try to get your papers in there. Go to the conferences. Yes, creationists should do that. Absolutely.
You're overly optimistic. The two, Perldum and Sanford and so on, yeah, they managed to get a few things published, but by and large, they give up after a while. I know Sanford, he had a status at Cornell University, and when they found out about his involvement in this creationism, that was taken away. They basically removed that status that he had, and he was no longer able to use the facilities at Cornell University, etc. So, yeah, a few of us sneak under the wire. I know there's a few that do that, but by and large, they don't know where we stand. They're unaware of where we stand. The papers are good, they're published, but they're by and large very few. And I can give you, like I say, 5 books, lots of cases, lots of documentation that indeed we've had many creationists who publish, and the evolutionary community finds out that they published, storm of protest, and the publishers were withdrawn. Many, many examples of that. After a while, you just feel, is it worth it to send papers in that are well done and to end up being rejected? Or often, is there no, don't even respond to the paper that's sent in. And so too many of us have had too many experiences with that. We've had, you just, why kick yourself in the rear by doing this? Because by and large, Sanford discovered, yeah, he's gotten a few things published, but by and large, he's discovered that they're not welcome. They do not welcome him in the journals. And then, of course, evolutionists brag that, well, gee, we don't publish in the scientific journals. Yeah, because it's very difficult for us to publish in the scientific journals. And again, this presentation I gave, I didn't mention anything about the age of the earth. I didn't mention anything about that issue. In fact, many creationists are not young earth. In fact, most creationists are not young earth creationists. They're old age creationists. I have a problem with that, but that's another presentation. But nonetheless, that is separate from whether or not they accept the creation worldview. And I don't know what percent, but I know surveys have been done and find most creationists are not young earth creationists. But on the other hand, that's a separate issue. Sanford, as far as I know, he's not. And so therefore they still have problems. Michael B. has had a number of problems. He was lucky a few times. His books sell well. And so he got published by a number of good publishers because his books sell well. But on the other hand, the reviews are terrible. They basically, all the reviews I've read of Behe's books are basically, he doesn't know what he's talking about. He's wrong. How did they publish this, etc. They're very, very negative.
Can I just get in for a second?
Sure,
I mean, Michael Behe is still a tenured professor, or what? I think he may be retired, but he's a professor at Leahy. He was never punished professionally for his. Everyone knows about his affiliation with Discovery Institute. There were no professional repercussions for him, and he continued, to my knowledge, to publish his biochemistry work separate from his intelligent design work. The only ID paper he tried to publish was Behe and Snoke way back in 2004, I want to say, and then it's all his kind of perfectly reasonable biochemistry stuff, but he's not trying. I mean, but Oster, Cordova, Basner, Sanford, they had stuff published just within the last few years. You said a bunch of people have, gotten fired. Like, can you name faculty members that got fired because they published creationist papers?
I got a list of 200.
Can you name any of them off the top of your head?
Oh, there's so many. So many.
Can you name any of them?
Out, and it's been a while since
I mean, everybody should this is not relevant to the debate topic, but now I'm just curious, like, if this is a thing that happens all the time, we should have some
basically, all of Behe's rights have been taken away. They have not fired him, but they have a note on the website basically saying that he's a faculty here, but we do not agree with him at all. And you look up.
Well, maybe, gentlemen, if
I think Sternberg,
in terms of the topic, common design.
Yeah, Donnie, just one thing. Somebody in the chat said Sternberg. He wasn't faculty. He wasn't like a tenured faculty person. I think he was a Smithsonian guy, wasn't he? Yeah. So he wasn't a tenured faculty. That was a different thing. But like Behe, there were no professional. Like, he kept his tenured position and taught classes through that whole time.
Yeah.
Well, let's do this, gentlemen. I'll jump in. That is a little bit over 20 minutes. And since Jerry was leading the way, Dan, let's largely give you the last word there. And our audience has been excellent in terms of on-topic questions. There's a lot of questions of clarification as well in terms of subject matters that you guys have been discussing throughout the debate itself. So let's jump right into our audience Q&A. And then we'll wrap everything up with concluding statements. That'll be a good time to wrap up our thoughts and points and solidify our cases for tonight. And so, gentlemen, it looks like we got a pretty good mix of questions for the both of you. Therefore, you'll both get opportunities to have the last words. How we have this structured is whoever the question's for will get the first roughly 2 minutes to respond. Then the other debater will get 2 minutes to respond/rebut, and then whoever the question was for gets the final word. And so, okay, let's now jump into some of these questions. I think this would be a good one to start off with, Dan, because if I remember correctly, you did bring up a couple examples of beneficial mutations that I do think would be worth engaging a little bit more.
Mhm.
And so the first question, solidify your faith. The question is this: what is an example of a beneficial mutation? Are there more beneficial or deadly mutations? So it's kind of 2 in 1. Feel free to list off, a couple that you really like to focus on, Dan, and then
Yeah.
feel free to answer the second question. Go ahead.
So let's start with the second half of that first here. There are deadly, I don't know, because lethal mutations are, a mutation that is necessarily lethal is going to be tough. Those are pretty rare, I would say. But in terms of a distribution of fitness effects is what we're talking about here. You're going to have most mutations the vast majority of mutations don't have a discernible effect on fitness or well-being, both in the evolutionary fitness sense and in the just can you function sense. There are more deleterious mutations that are a net harm to fitness than there are beneficial mutations. But as Kimura illustrated, if you have beneficial mutations, selection does its thing, as long as you have a population size that is sufficient to override drift. So it's the ratio isn't what matters. There's other parameters there that matters. But in terms of examples of beneficial mutations, I love the mutation that we see among Tibetan populations for blood oxygen saturation. That is a novel, or it's actually 2 alleles that the Tibetan populations have. There's a similar thing I always forget the island, but I bet somebody in the chat can remember the island where you have the divers that are able to saturate, I forget what organ it is, but they're able to saturate their organs with red blood, oxygenated blood, and so they can stay underwater for over 10 minutes. That's a really interesting one. Lactase persistence, the ability to digest lactose throughout your life. There are 2 main mutations that are responsible for that. And then there are a bunch of much rarer ones. Those are unquestionably beneficial mutations. The lactose thing that you always hear from creationists is that their loss of regulation of the lactase gene. That's not true. The most common ones are an upregulation due to increasing the affinity of an enhancer for transcription factors. So all of those are examples of new mutations in humans that are beneficial. There you go.
Appreciate that, Dan, and great timing. That was 2 minutes basically on the dot. A couple that you brought up: blood oxygen saturation, beneficial mutation, Tibetan people, I believe. Lactase persistence. There's a couple of the few that you brought up. So Jerry, let's now throw it over to you. And you also have 2 minutes to respond, starting now.
From my research, the beneficial ratio between beneficial and all mutations is 0.04%. And most of these beneficial mutations were not beneficial for the person or organism mutated. Was beneficial for humans, like seedless fruit is a good example. So 0.04% of the literature, this is just looking at mutations, how many are listed as beneficial, how many are listed as detrimental. So it's 0.04%. So it's a very, very small percent. The problem is just like going up a hill. You take 1 foot up the hill and 6 feet backwards. Take 1 foot above the hill, 6 feet backwards. We end up again with genetic catastrophe, and you see this in life, you see this in animals, you see this in medicine. It's true you have a few cases where you have what appears to be a beneficial mutation. On the other hand, a lot of these are not significant in many ways because we're talking about minor changes. We're talking about one gene is broken and therefore allowing other genes to express, or minor mutations in enzymes to occur. So therefore, the organism can break down nylon, even though nylon is very similar to other compounds. And one or two mutations can basically cause the enzyme to be able to break down nylon as well. So there are a few that's not debated. The problem is there's so few, they're so rare that they're just swamped by the harmful mutations. And when I should look at just the beneficial mutation for the organism, it's probably more closer to 0.0004%. So it's a very, very small number of the total of mutations.
Thank you, Jerry. That is 2 minutes. Dan, the question was for you. Therefore, you get the final 1 minute. Go ahead.
Yeah, so I forget the exact numbers, but in my paper with Zach, and I'll give Zach all the credit for doing the actual math here, but we used an empirical distribution of fitness effects. So looking experimentally at the ratio of good to bad mutations and using that as the basis. And we showed that the math for genetic entropy doesn't work given that empirical distribution of fitness effects. So whatever that ratio is, like when you empirically determine it, the math doesn't work. You don't get genetic entropy, genetic degeneration, whatever you want to call it. I also none of the examples I gave are examples of where you break a gene. They're all examples of some novel functionality that's beneficial. And just to tack another one on there, there is an anti-malarial mutation in some humans that it's separate from the sickle cell allele, which obviously comes with a cost if you're homozygous for it. This other allele confers resistance to malaria without that cost. That's unquestionably a beneficial mutation. So plenty of examples. Yeah.
Thank you very much, Dan. Appreciate that. Few response question there. Very good and helpful to elaborate on portions of the debate here. So let's move on to the next one. This one is now for you, Dr. Bergman. Comes in from Andrew Cumming. Andrew, appreciate the question again. We've had a good mix of both sides in our live chat tonight. So question for you, Jerry. In what ways can common design be specifically tested and falsified with regards to homology and anatomical comparisons between species?
Well, as I've testified, I've evaluated basically by looking at the design. Is it functional? And is it possible that that design could have evolved? Is it possible that design is related to other organisms? And I found in case after case that indeed there are good reasons for the design that exists, and these good reasons cannot be explained away by homology or anatomical comparisons, etc. They are unique in many ways. And the tongue example I gave earlier, but there are many other examples as well. Primarily, I'm looking for the evidence of design and the likelihood of that design evolving. And that may not be a traditional hypothesis, testing hypothesis, etc. But on the other hand, I guess my hypothesis is this functional design? Can this design evolve in small steps? And so many designs I look at cannot evolve in small steps. For example, right now I'm working on a paper which deals with the carriers from one cell to another cell. And these carriers indeed have a very unique design, very important. Without these carriers, as the paper I'm reviewing is looking at, without these carriers, life could not exist. They're required for life. And yet these were unknown pretty much, and because they're so small partially. And now just in the past few years, we're discovering these carriers are complex, well-designed, and necessary for cellular communication as well as for other things. And so indeed, this supports the idea of design. It also supports the idea that this couldn't evolve because life could not survive. As far as we know, all multicellular life uses the same design. And therefore, this supports the creation, intelligent design worldview.
Thank you, Dr. Bergman. Dr. Dan, you're up for your 2 minutes. Go ahead.
So what we just heard, folks, was basically an irreducible complexity argument, which is not actually an answer to this question, because the question is about testing specific hypotheses with regard to homology, but addressing irreducible complexity, where you can't evolve a thing step by step because you need all of the components of that system in place in order for that system to function. That's not a real thing, because we've directly observed the evolution of systems that meet the criteria for irreducible complexity. And this comes from Michael Behe. This is kind of his concept from Darwin's Black Box from 1996, I want to say. The examples that we have, for example, the Lenski long-term evolution experiment, the CIT plus line, the aerobic citrate metabolism trait. That's an irreducibly complex trait. And bonus, a creationist, Scott Minich at University of Idaho, I want to say, wrote the paper that showed that it's irreducibly complex, that you need all the parts for it to evolve, but we directly saw it evolve. The HIV-1 VPU protein is able to antagonize, which is to say neutralize, a protein called tetherin in the human immune system. That trait requires at least 4, possibly up to 7 specific new mutations. If they're not all there, the trait is absent, but it clearly evolved because HIV appeared in humans just within the last century or so. We also have several examples of new endosymbiotic organelles with gene transfer. So you have a gene going from the bacteria or the algae into the nuclear genome, expression of that protein, and then back to the organelle. Now you could say it was created that way. That specific species was created that way. Okay, but there are animals with that, which means we're doing species level creation, which is again a non-starter for most creationists. So I think we would agree, because most creationists, I don't know about Dr. Bergman, but most creationists reject species level creation, which means we would agree that within a kind, you have this new endosymbiotic organelle, which requires irreducible traits to evolve.
Thank you very much, Dr. Dan. Dr. Bergman, this time you get the last word because the question is for you. You get a minute. Go ahead.
Okay, I forgot what I was. Oh, again, you're swamped by the negative mutations is what, and these examples, yeah, you get minor examples that, of course, support your idea. In medicine, what I wanted to say was in medicine, we don't sit down with a formal hypothesis and conclusions. The hypothesis is, given this medication or treatment, the patient will heal faster, get better sooner, will have less side effects, etc. And so it's very clear, and so therefore we don't have to bother with a hypothesis because it's pretty obvious. The medicine works or it doesn't work. The therapy works or it doesn't work. And works means basically improvement. Symptoms are less severe. Long-term treatment is effective, etc. And so I guess we don't normally think, and we do indirectly think of hypothesis. We test it and we come up with a conclusion. But it's not set out formally in those terms.
Okay, that is 1 minute. Gentlemen, appreciate the engagement on our second question there. We're now back to a question for you, Dr. Dan. Comes in from Beyond Doubt Theology. Question for Dan. What is the best experiment you can point to for the most substantial macro evolution? Not just homology and comparisons, but actual experiments. Thanks. Thank you.
Oh man, I love this question. There's so many good ones. So one of my favorite ones is the evolution of de novo multicellularity in a species of green algae that has no multicellularity in its evolutionary history. And over the course of about 2 years in the lab, they evolved into an obligatory multicellular state where they had no unicellular stages in their life cycle. So that was the de novo evolution of multicellularity. And it wasn't just that individual cells accumulate in a colony. It was that a single cell, they divide and they stick together and they form a multicellular structure, just like we do. So that's a really good one. I also love the experiment where, no, it's not just a colony for the chat. I also love the experiment where they, by changing no new genes, no new information, but just a change in the expression pattern of 2 regulatory genes in crocodiles, allowed the crocodiles to grow feathers. So instead of developing scales on their skin, they develop feathers, which is a new morphological trait. Donnie, I forgot to hit my timer on this one, just FYI. So that's a brand new morphological trait that's only seen in the avian reptiles, but we were able to cause crocodiles to grow feathers as well based on some very minor changes. And then it's not an experiment, but it is a direct observation in nature. We have lizard populations that are right now in progress, converting from laying eggs to giving live birth. That's macroevolution by anyone's standards, I would hope. And just throw one more in there, the endosymbiosis that we've seen. We've got an amoeboid rhizarian becoming a brand new, never before seen type of green algae. I would think that is macroevolution by any reasonable standard. Again, this is an event that's happening in nature, not an experiment, but we are directly observing it.
I don't know how you did that. That was 2 minutes on the dot. I guess you're just used to taking 2 minutes to answer these questions. So to help in terms of Jerry, you get a 2 minute response. And so Dan, what I noted there, de novo multicellularity in algae species. You pointed out it's not a colony. An expression pattern in crocodiles, allowing the crocodiles to grow feathers rather than scales. That's an interesting one. Lizard populations converting from laying eggs to giving live birth, and also endosymbiosis. So I appreciate those examples in your 2 minutes. Very helpful in terms of engaging in this debate. Jerry, let's give you 2 minutes.
I'm not aware of these examples. Maybe you'll send me information. I could look into them, but the ones I looked into of the so-called feathers on dinosaurs are problematic. And so I have a feeling that the so-called feathers on crocodiles are problematic, but that certainly would be an interesting one to look into. And I'm sure creationists will love to deal with this. So if you let us know information on that, and I'm sure that creationists will love to get into this because they love to look at these examples and see whether or not indeed the literature does indeed support the claims. So please send me information.
Was the example, Dan, that you pointed to with the crocodiles? Because Jerry, I noticed you mentioned dinosaurs to birds, but was the example you put forth, Dan, did that have to do with something that was tweaked in the lab to make that happen? Oh, Dan, I think you're on mute.
Yeah, this paper is called Multiple Regulatory Modules Are Required for Scale to Feather Conversion, Molecular Biology and Evolution, 2017. I'm going to drop a link in the chat here. Or not a link, but just a reference. I put the link in the chat, in the private chat on StreamYard here. The link is the multicellularity algae paper, and then the reference below that is the crocodile scale feather thing.
Okay. I'll put those in the description box. And Jerry, we can also send you that. Dr. Dan, you might want to send your paper that you wrote with Dr. Hancock as well.
Yeah, we'll do.
As that's directly related to a few things discussed during tonight's debate, and Dr. Bergman might want to interact with that at some point in the future. And so, okay, well, technically, Dan, you get the last word. So if you wanted to say anything quickly before we move on, go ahead.
Just let me think of let's think of some. Lizards with placentas is another example I can think of. Again, not lab, but directly observed. And the reason this matters is because, again, if creationists want to say they were created with the placentas, then we're doing species level creation, which I can't think of any creationists that are down with species level creation. So the lizards with placentas is another really good example of directly observed macroevolution. And because it's a specific species within a kind, we should agree that that's a thing that's new since the flood.
Okay, appreciate that, Dan. Okay, so that was a question for you, Dan. And now let's grab you a question, Jerry. And this one comes in from Dr. Chris Thompson. Appreciate the question here, Chris. And again, appreciate all the engagement from our live chat tonight. It's been a good technical, thought-provoking debate tonight. So Dr. Thompson has a question for you, Dr. Bergman. And the question is this: how do you explain the emergence of unique novelty and adaptation in a particular species within a kind if mutations are always deleterious?
Now, I didn't say they're always deleterious. I said the majority are. And so, yeah, there's going to be a few beneficial changes. And I don't deny that. That's clear. And so the emergence of unique novelty, again, when I look at most of these, I find the explanations relatively simple. And again, there's a few I missed. So it's good that Dr. Dan is on here and I can get a few more examples to look at, and the creation community likes to look at these. But I find in the past, I've got 2026 6 articles now. When I take these claims and analyze them in detail, I find, at least the ones that I've looked at, without exception, they support the creation worldview. So I can't imagine every one of them supports the creation worldview. Certainly some don't, but I have not run across any yet that don't. And so therefore, I like to see them. I like to be able to review them.
Thank you very much, Jerry. Dan, you get 2 minutes.
I'm not really sure what I can add here. Right, we should be able to agree that there's like new traits that appear in things that are not harmful. If we can document that there are new mutations that occur within a lineage with something that we agree shares common ancestry that leads to new beneficial traits that are, adaptive in their environments, then there's that old joke where the punchline is, well, we agree, now we're just haggling over the price, right? Once you allow beneficial mutations in, the creationist math like no longer works, and it's kind of intro level population genetics why it no longer works. You can go back to Kimura's famous 1979 paper, and he in that paper explains why when he was talking about genetic drift, which is to say neutral accumulation of he was modeling drift, which is a process that randomly removes variance as opposed to natural selection, which non-randomly results in a loss of variation. He explained why he excluded selection from his calculations, from his model. And it's because once you allow selection in, even just a little bit, then it runs away and takes over. So as long as you have beneficial traits in there and the population is such that it's like selection can occur, it's not sufficiently small that you only get drift, then that population is viable and you can get new adaptations, which we have directly documented.
Thank you very much, Dr. Dan. Dr. Bergman, you get the final minute to respond. Go ahead.
Well, again, there are beneficial mutations, and my survey is 0.04% from what I've looked at. So there are some there, but again, overwhelming majority are deleterious or near neutral. And so therefore, this is a major problem for evolution to explain what we see. Again, you're going to find a few things out there that are hard to explain. And but again, my experience is in looking at hundreds of these, indeed, in the end, when you look carefully into the data, you find out it doesn't support the evolutionary worldview. So again, I look for these, of course, and I try to find them. And so the ones that Dan just mentioned are excellent. They make great papers. And I'll look into them and see, indeed, does the evidence support what the claims are, and then do a paper on them. So I've been doing that for 40 years, so a few more are useful.
Okay, thank you very much, Dr. Bergman. All right, gentlemen, so that was 2 each. Let's go 1 more each, and then we're going to jump into our concluding statements here. And so, okay, Tanya Brown. Now we got a question for you, Dr. Dan. And so she says, Baum dismissed common ancestry because of the statistical implausibility of convergent evolution. How is that relevant to young Earth creationism?
Because in order to get the nested hierarchical pattern, you would have to get, right, you have this group evolving independently, created kind. You have this group evolving, created kind. In order to get the nested hierarchical pattern, you would have to have the correct ratio of shared and not shared mutations, and not just in group A and group B, but then also in C, D, E, F, right, as you go up in the hierarchy. So it's not just dogs and wolves, it's dogs and wolves and coyotes and foxes and da-da-da-da-da, in whatever pattern that you propose. So you would have to, by chance, have a very precise pattern of shared and unique mutations across each of those lineages, such that by chance you arrive at the evolutionary nested hierarchy. And the key thing here, the key implication, is that because each group, at whatever level you want to say, was created independently, because each group was created independently, you can put whatever pattern you want. You could have them preloaded with whatever pattern of variation you want, but it's only going to be either 2 individuals or 7 whatever the number is, getting off the arc. It's for a few, it's more, but for most, it's 2 individuals getting off the arc. So all of the existing variation within each group has to have been generated post-flood, because for each location in the genome, you could have at most 4 alleles, 2 per individual. So the reason that statistically we can reject separate ancestry based on the implausibility of convergence is because you need to converge not just on this or that specific mutation, you need to converge on a consistent pattern across all of those genomes.
Thank you very much, Dr. Dan, for that response. Dr. Bergman, you now have 2 minutes. Go ahead.
Yeah, it's a good point. No, I really have no objections to that. Again, though, we're looking at the fact that organisms are swamped by the deleterious mutations or by near neutral mutations. And a few examples, it's nice to know a few examples go the other way. And there's probably more examples. But again, I like to get a hold of these and look at them. And so far, my experience is they don't pan out when you look at the data very carefully. So, but on the other hand, I'm challenged by these. And when I become aware of them, I love to look into it and see indeed what's the evidence for crocodiles developing feathers. That would be a very interesting paper to look at and to evaluate. And as a whole, creationists, they love to look at these examples and write about them. So it's a challenge. Makes life interesting to have such challenges.
Thank you, Dr. Bergman. Dr. Dan, you get the last minute. Go ahead.
Last thing I'll just mention here regarding the I forget the exact phrase that Dr. Bergman used, but the accumulation of harmful mutations. There are at least 2 papers in the literature that directly refute that notion. One of which I alluded to earlier. It's called Springman et al. 2010. Evolution at a high imposed mutation rate. Adaptation obscures the load. And then the other one is the paper I co-authored with Dr. Zach Hancock, Back to the Fundamentals, a reply to Basner and Sanford 2018. And that was published last April in the Journal of Mathematical Biology. And both of those papers are direct refutations of the concept of genetic entropy.
Dr. Dan, I appreciate that. Can I cheat and ask you this and maybe give you each 30 seconds to respond? So, Dan, your paper that you've brought up a few times, Back to the Fundamentals, a reply to Basner and Sanford 2018. I will link that in the description box. I think that paper deserves a read. Congratulations to you and Dr. Hancock on getting that published. Can you provide, let's say, a minute summary of the major points in that paper and how they counter the nearly neutral problem? And then we'll give Dr. Bergman an opportunity to maybe give his thoughts.
Yeah, so the short version with this paper, and I'm obviously biased. I really like this paper. I think it's awesome. I'm biased because, I helped write it. But the short version is this. When you look at, so there's a part of it that has to do with Fisher's fundamental theorem of evolution with natural selection. That's not directly relevant to the genetic entropy part. The genetic entropy part is taking an empirical distribution of fitness effects rather than a theoretical one. Sanford, to show genetic entropy, uses a modeled distribution from Kimura from 1979. We, and by we I mean mostly Zach, he did all the math. He deserves all the credit for that part of it. Using an or more than one empirical distribution of fitness effects, which based on actual numbers instead of just what's in Kimura's head, we showed that what Sanford says happens doesn't actually happen. When you model it using the empirical distribution, you don't get inevitable extinction due to the accumulation of slightly deleterious mutations that are below the selection threshold.
Dan, I appreciate that. I posted the paper in the live chat in order that people can check it out and interact with it. Dr. Bergman, anything you wanted to add to that or any thoughts you wanted to provide on the issue?
Yeah, I'd like to look at that paper and see what he had to say. I'm skeptical because, again, the 3 degrees I have from medical school, our direction was very clear and how to deal with it was very clear. And cancer is a good example. Where it's increasing in the population, where medicine has to deal with these issues. And that's one one reason that we exist is to deal with the accumulation of mutations and try to come up with some way of getting around the deleterious effects that these cause.
Okay, thank you, Jerry. And Dan, you get the last word. Go ahead. Oh, Dan, I think you're on mute, but it looked like you said you're good.
I mean, yeah, no, that was just a summary of the paper. I don't have anything to add. Yeah, it was just a little brief summary.
All right, very good. Appreciate that. And so, gentlemen, we are now moving into our final question.
Hang on. I think that was the third question for me.
So one more for Jerry. Yeah. So we got one more for you, Jerry. 3 each. Very good audience Q&A. Again, I always look forward to these as they help us to make the debate that much more comprehensive and edifying to our audience. And so, Jerry, this one comes in from Dr. Joel Duff. Appreciate the question, Joel. Dr. Bergman, how many generations do you think it would take to design a mastodon and a mammoth from a common ancestral pair? So in other words, if I'm interpreting it correctly, Jerry, from the young earth creation position, you'd say there was an elephant-like kind on the archetype, and you would have gotten these various species from that ancestor. And so go ahead.
I didn't know there was that much difference between a mammoth and an elephant. I don't know that much about them, but from what I'm aware of, mammoths, basically, and elephants, there's a lot of similarity. And 1 or 2 generations, I assume, would produce the difference. But then again, I don't know. So interesting question, though.
Okay, very good. Thank you, Jerry. Dan, anything you wanted to add? And you can also elaborate on what Dr. Duff is saying here as well, if you'd like.
Yeah, I think so kind of you have kind of 2 ways of approaching this, right? You could, from the design perspective, you could front load, right? We have the starting pair and then it has to diversify, or you could have ongoing tinkering to make specific mutations happening. Now, most creationists reject the tinkering hypothesis because it's untestable. It's just miraculous intervention in an ongoing fashion. You can't evaluate that. Now, if you were to have the starting pair and then get your descendants within a single kind, the problem with this is not that you have 4,400 years. It's that you have from the flood to Middle Kingdom Egypt, which is like 1800 to 2000 BCE. So you don't have 4,000 years. You have 400 to 500 years. And about 100 years of those in the creation model are an ice age. So with long-lived organisms like the elephant kind, you basically need to have the kind of like the cartoon version of evolution that like Kent Hovind thinks is like, oh, did cow give birth to a monkey, right? Like each generation, because of the long generation times, would have to be a new species. Because like by the time you get to Middle Kingdom Egypt, we have direct documentation of all of the different species in various kinds, right? Cats, for example. Right. So that's the problem here, is that you just don't have enough time to go from point A to point B in the creation model, especially for things like mammals that have long generation times.
Appreciate it, Dan. That was basically 2 minutes. Jerry, the question was for you. And again, this is the final question for our debate and specifically our audience Q&A for tonight. So Jerry, you get the last minute response. Go ahead.
Well, we've seen some relatively quick changes from one organism style to another. And so I don't see it to be a problem in a couple generations, 4, 5, 6 generations, from an elephant evolving into a mammoth or a mammoth into an elephant. I don't know, maybe a mammoth and the elephants were on the ark. I don't know. Maybe had baby elephants that were pretty small. Maybe that would have been, another creationist who like to debate about what was on the ark, etc. And to me, it's speculation. We don't know, but certainly no problem with small animals. You don't have to bring a full-grown dinosaur in. You can bring a dinosaur that's 3 feet tall, and so that's not an issue. But I guess these are things I try to. They're not in my purview, some creationists focus on these, and I focus on other things which are more easy to defend. Not that they don't do a good job. I mean, the arc, I think, is every evolutionist should go through the arc and at least see what our side is and see what our view is. By the way, some creationists don't agree with what they try to show in the arc. Some creationists believe the arc itself was very differently designed than the arc that's in Kentucky, and which it could well be. And I have friends that feel it's very different, actually, than the arc that they show in Kentucky. But it's an interesting debate, and it's not one that I really focus on. So I'm broad enough in my interest, so I don't want to be too broad and know everything about nothing. Is what concern is. So I try to focus on the fossil record, on the whole question of mutations and the harm that evolution has done, and that's my main focus. And I seem to be pretty busy looking at those few areas.
Okay, Jerry, appreciate that final minute response. Dr. Duff, thank you for the question. And gentlemen, that concludes our audience Q&A. Excellent job to our audience. Thank you so much for so many great questions, very much on topic questions. We do have 5-minute concluding statements. So again, this is a good opportunity to wrap up anything we feel may have been left hanging and to essentially land the plane, bring everything to a safe conclusion regarding our specific positions tonight. Dan arguing for common descent and Jerry arguing for common design. And so let's do our best now to conclude everything and give our audience everything necessary to examine the debate in hopefully an objective manner. Dr. Dan, we're going to give you the first 5 minutes for a concluding statement, and you're good to go. The floor is yours.
Thank you. Thank you, everybody, for being here. Thank you for the questions. Those were really fun questions. So to wrap this up, we meandered a little bit from the topic that we initially were talking about, and that was totally fine because that was a really fun conversation. Now, if you think all the way back to the top of this, I brought up a couple of papers that actually directly tested this question, common design versus common descent, based on directly observed data. And those papers overwhelmingly showed how only common descent is compatible with the evidence. Dr. Bergman didn't address those papers. And as far, as we should all be concerned, that's pretty much it. Because again, YouTube is silly. It's fun. But it's not where like science and science debates happen. It's, we don't settle things here. We settle things in the peer-reviewed literature. And it is a settled question in the literature. And I again invite creationists to publish their work and show otherwise. But we talked about information. We talked about genetic entropy. We talked about generating new traits. And all of that was a lot of fun. It was, your typical kind of creationist fare, which I always enjoy. And I showed how and Dr. Bergman agreed that we can increase information. You can have new beneficial traits. And we didn't agree that we've directly documented what you might call macroevolution, but I think it's pretty clear cut that we've done that, even though none of those were the topic of the debate. So I do just want to wrap this up by going back to our actual debate topic, our actual question of common design versus common descent, and how we can tell them apart because they make competing predictions that are different from each other. And I want to remind everybody that whether you agree with whether the phylogenies I showed are correct or not, Dr. Bergman agreed with me on the different competing predictions and also showed that we cannot tell the phylogenies apart across different kinds versus within a kind, despite those competing predictions that we agreed on. And for tonight's debate, that's really it. Science is about competing predictions and testing those predictions. We have two hypotheses. We did a test of those two hypotheses, and what we found tonight was that the hypothesis from common descent was accurate, and the hypothesis from common design was wrong based on the predictions from those two hypotheses. So that tells us for the topic of tonight's debate, common descent versus common design, we showed, and I say we, not just me, but me and Dr. Bergman, together with those predictions, showed that the answer is common descent. Thank you, everybody.
Dr. Dan, thank you very much for that 5-minute concluding statement. Dr. Bergman, we're now going to hand it over to you. I will reset the timer, and you have 5 minutes. Go ahead.
Okay, we didn't spend much time on the fossil record, but that's one area I have a lot of interest in the fossil record, partially because a lot of studies out there, many studies, and comparisons can be made. And from my evaluation of the fossil record, over and over, I find that indeed it does not support the common ancestry of most forms of life. And I've looked at reptiles, I've looked at bats, I've looked at birds in general, I've looked at parrots, I've looked at so many mammals, I've looked at humans, of course. I have a whole book called Apes as Ancestors, and it's pretty clear from my research looking at the published literature, pretty clear that indeed the progressive idea is being disputed and slowly replaced by basically we didn't have a progression from apes to humans. We have a huge amount of variety in the fossil record, and it's very hard to get a lineage from apes to humans. In fact, it's almost impossible. What we see is, I think my voice is starting to give out. What we see is an enormous amount of variety of extinct primates. And so it's pretty clear, and I will keep looking at different animals to see what indeed the fossil record says. But from the ones I've looked at, the fossil record is very clear that there is no evidence of common ancestry for any of the fossils I've looked at. And this is, again, a review of the books on evolution. A good example is snake evolution. I don't have any idea where snakes came from. I did a paper on snake evolution showing indeed the herpetology evidence is quite clear. And one of my colleagues who got his doctorate in herpetology, I said, would you like to look at this? And he said, no, I don't care to. I said, why? He said, well, because snakes evolve, period. And therefore, there's no need to look at your paper. But I stressed to him that the literature I consulted quite clearly basically said we have no evidence for the evolution of snakes. Of snakes. We have a lot of hypotheses, theories, speculation, but no direct empirical evidence of the evolution of snakes. And we covered the so-called limbs that they have, what they were thought was the degenerative limbs. And these are pretty clearly copulatory. Boy, my voice is giving out. These are quite clearly copulatory organs, and they are not vestigial limbs. Maybe there's a message to me to not continue, but anyways, I keep looking at examples of the fossil record, trying to find indeed, are there any good examples of the evolution of a common ancestor in the fossil record? And I have yet to find a single example, even among humans. Now, some people you can see in the background there, my book, Apes as Ancestors, some people may question that. What I did in that book was look at the published paleontological literature. And what I found was quite clear. The published paleontological literature has clearly refuted all of the theories of human evolution. Now, what happened is that I have my theory, you have your theory. I think my theory is supported. You think your theory is supported. And I refute your theory and you refute my theory. And so basically what we looked at was the critics of each theory. And so we found basically that the critics of each theory were very effective in showing that they're wrong. Now, of course, as a whole, these people believe that human evolution occurred. They just can't agree on how. But nonetheless, I think it's a pretty good case that the literature makes that all of these theories, these hypotheses are indeed not supported by the evidence, the fossil evidence. And so I've looked at probably with fish, I've looked at bats, I've looked at birds, I've looked at mammals, I've looked at primates. We're still stymied as to fossil record for gorillas. I looked at the claims and we don't know where gorillas came from. We know they evolved, but we don't have any evidence in the fossil record for the evolution of gorillas. And so it's pretty clear from my review, and I've been doing this for 30 years, my review of the literature shows that the fossil record is very clear. There's no evidence of common ancestor for the living creatures we have today on the earth. By the way, the most common belief is that we evolved from sponges. So that's the commonly accepted idea that we
10 seconds.
Sponges. And so that I think is problems, but on the other hand, it's interesting that we've finally gotten down to that. That's the latest theory.
Okay, Dr. Bergman, Dr. Dan, thank you very much for those concluding statements. Gentlemen, that wraps up tonight's epic debate on common design versus common descent. Again, I appreciate the time that you've given to us for tonight. And I also want to thank you both for a good, engaging, professional, and I got to say, cordial debate. You both gave me an easy job tonight in terms of moderation. So we're going to let you guys out of here for the rest of your weekend. So I want you guys to enjoy yourselves. Dr. Dan, Dr. Bergman.
Okay, so that was my debate on common descent versus common design with Dr. Jerry Bergman. Like I said, I am happy with how that went. I accomplished what I wanted to accomplish. So thank you for watching. I will see you next time. Don't get fooled.